Um, share. We should finish up section 4.2 today. There was a few problems I wanted to go over and a little more explanations, but on page 212, there's a question 1 that I wanted to go over. Where's it at? There it is. I guess I can make this bigger. On this flow rate here, so they were talking about a nonlinear function, what happens when something's not a straight line growth, because then it doesn't stay the same amount. And if we look at this here, this is the logistic model of the flow rate. Notice at first, the stock, as it's increasing, the flow rate's increasing, but then when it hits a maximum, the flow rate or the amount going out is decreasing as the stock level increases. So it's the ones we've dealt with before were always a straight line. It was a consistent growth or decay. Here, part of the time it's increasing, and then the second half of the time it's decreasing. And so then that changes your value, or plus or minus here. So when the stock is increasing for the first half, this would be increasing the inflow. But then once this has reached its high point, then it starts decreasing. It would be a negative. So for the first half, it's a plus. For the second half, it's a negative. Any questions on that? I think that's the main part it's showing you there. But on a lot of different like coal, oil, a lot of different things we can use. It's called exponential growth. That most of them were exponentially growing, but this one now has that decrease in it. Because once you hit a high point, you have to start slowing down or you're going to run out. And that's what it's showing you. Any questions on that? That high point we saw in the parabola, the graph that went this way. This high point is the peak, is where there's the peak flow rate. The highest or peak flow rate is in a logistic model occurs when the stock level is exactly half of the carrying capacity. So if we look at that graph again. C is the carrying capacity. And when we hit this high, that is our peak flow rate. That's the most that will increase, and then it's going to start decreasing. That's the highest or peak flow rate, and that is when your capacity is at half. So if it can hold, it was 100, I forget that. the fish in the pond was like 100 million or something like that. It would be half of that. But it's the S-shaped curve showing the accumulation of stock in a logistic model is called a logistic curve. And they say S-shape, but this one was an upside down parabola. An important example concerns the extraction of a non-renewable resource. Suppose that a certain quantity C of a resource, iron ore, coal, oil, or something of that nature, is available in the ground. The process of mining and extracting the resource can be represented by a stock flow diagram with two stocks, one for the unmined and one for the mined. So this one would still be in the ground. This one is what we've extracted or taken out from the ground. Since this is one of our stocks, this is the in-ground stock, this is the out-of-the-ground stock. When you're leaving the stock, it's a negative. And it's leaving by extraction. And then extraction is increasing the one that's out of the ground. So this would be the extracted oil or whatever we are removing from the ground. So this is a stock and this is a stock. This is coming out of the stock, it's a negative. When it's going into the stock, it's a positive. Any questions on the blue part? Did I start recording? I think I did. Didn't look like it was recording, but it is. Now the red arrows are going from both of the stocks to the extraction. The reason they're a plus is the more we get extracted, the more money we have, we can build better things, and we go back and we extract more. And it kind of explains it down here. There are two influences that are going to be important. The more of the resources has been extracted, the more profit in the mining will be made, which then encourages more extraction. And then on the other hand, it's like encouraging new players to enter the market. This influences an example of the capital investment feedback loop. It is represented by the right-hand amplifying feed loop, this one, which would be, since there's no negatives, amplifying. The more we take out, the more money we have, better resources, and we mine even more. And it just keeps amplifying. On the other hand, no deposit of a resource is completely uniform. It naturally contains both rich and poor sections. In the context of oil, for example, rich areas might be gushers, where the oil naturally spouts underground, and the other may need fracking. But in any case, the more resources that we find under here, then that's going to increase extraction. So an increase in resources increases extraction. And the more we extract, the more money we get, which then causes more extraction. So that's why both of these are positive. If the resource underground increases, then they're going to extract more. If we extract more, then we have more money to extract even more. This loop would not be amplifying, it would be stabilizing because there's one negative, so this stabilizes where this one amplifies. Any questions on that? If S denotes the total amount of resources extracted, then C minus S is the amount remaining. Because remember, C is the total capacity that's in there. And so if S is the amount taken out, if you subtract them, it's how much is left in the ground. So the model we have sketched above suggests that the rate of extraction will be proportional to S times C minus S. So the amount extracted times the amount that's left inside. This is a example of a logistic growth rate. In a logistic growth model, the graph of the growth rate against the stock level is a straight line heading downhill. The x-intercept in this line is carrying capacity, and the y is the constant. So what they're doing here is making it into a straight line. Is the equation of a straight line with x is the amount to start with, and y is your rate. So this is saying that at time 0, this is the total carrying capacity. And then when the carrying capacity, well, y-intercept doesn't necessarily make sense in this one, but the rate is how fast it's growing or decreasing. And there's a good example on page 216. But this is one formula that we will use. So 216. No, they did the growth rate a little bit different than we did it. If we're going to graph it, we were finding the growth rate from always starting with the initial point. But what they did was find out how much it grew from each time interval. So it started with 0.99. It went to 1.96. So what they did was use the growth rate, but just from here to here. So if we took the new amount minus the 0.99 divided by 0.99, let me shorten this a little. That would get us the 0.98. But then for the next one, instead of using the beginning amount, they want to find how much it grew from 2 to 3. And so 3.85 minus 1.96. So instead of finding the rate from the very beginning, the starting amount, they're finding between each time interval. Carrying capacity is 100. I was looking to see if that was hours or does. Oh no, it's not saying. or I'm missing it. But anyway, these are the time intervals. And they want to find the rate between each time interval. Rather than the way we did it in class yesterday, we just started with the 0.99 and used it for the initial amount. Because it was the initial amount each time. But here they want to see how the rate is changing between each individual timestamp. Any questions on that? So to do a graph, you should use each individual timestamp because they want to show how it's slowing down. Notice it increases until it hits its halfway mark, and now it's decreasing. Oh, it's always. Now what they did was, is there any questions on finding the growth rate between the units? So if we look at 9 to 10, they got 0.16. You would take the 8366 minus 71, the amount that was there in the time before, and divide by that same one. And we would get 0.16. So you can see at first it's not changing by too much, and then all of a sudden it starts changing 61 to 44 to 28 by more. This only changed by 0.02. Now the graphs for the graph, first one, they plotted all the points. Stock was X and growth was Y. And so it formed this linear line. In the second one, they only graphed the first couple and then estimated the line. When you do not go further out on your data, that's called extrapolation. Should be a definition here. Right here. So we picked a certain few, but then extrapolation is when you're finding values that are outside of the data values you found, and they're not always as accurate. Notice this is hitting at 100 here. This is hitting short of that. 80, maybe 92, 93. But that's because we didn't go far enough out for an extrapolation. So it's just an estimate. It could be not as accurate. But if you find more points, then you're getting more accuracy. Any questions on that? Which one stabilizes? Okay. The stabilize is the one with the negative in it. So this one is stabilizing because of the negative. This one is amplifying. Remember, if there's an odd number of negatives, it stabilizes. Any questions on that? You're welcome. These graphs, they're having you use a formula to find the equation. But on Desmos, Oops, hit the wrong thing. So at Desmos.com, you can plot the points. To do that, you click here on the plus sign and go to table. And then you would enter your X and your Y. The X is the stock and the Y is the growth. So if we put a couple in, this first one would be at 0. So 0.99, 1.96. And then here we would put our Y. So this first one would be 0. Because it just started. And it plots our points over here. They're looking so close. You know what? Let's not put this one in. I don't think they put that first one in. There you go. I took that first one out because it's a starting point, but they don't have, it had no rate, so I just took it out. I'll just put one more. 1379. And this would be our graph. Now, notice how these are small decimals and these are whole numbers. Well, you can change your units. That way you can see the difference here better. And what you do is this wrench that's on the side. You can click on the wrench. And I always like to start with -1 unless my numbers are really big, and then I'll go with something else. But I like to start with -1 because it gives me the axis. And then you want to go past your largest number, which right now is 1379. But I'm going to go to 100 because that's my capacity. So maybe 102, so it's a little higher than it. And then this one will go from -1 to 1. And you could see the points, and this is kind of like that first one. But I guess the closer one, the one on the right. Now, to get an equation and to find out how strong the relationship is, this is x1 and y1. Remember, a straight line is y equals mx plus b. So it'd be y1, but then instead of an equal sign, look where your number 1 is on your keyboard and look to the key to the left of it. If you hit shift and that key, you'll see this little squiggly line. and then mx1 plus b. It gives you your equation, and this tells you how strong the data is to a straight line. And it shows you where it's hitting at 99.341, so almost 100. So that little squiggly line here is to the key to the left of the 1. You have to hit shift in that key. When you hit the Y1 and the X1, you just hit the 1, it'll subscript itself. The reason I used X1 and Y1 is because that's what it says in my table. Any questions on entering those? So then this gets you your line, it's right here. My y-intercept is 1. And the slope is negative 0.01. The more points I add here, it probably will change this. It definitely will move this, as we've seen here. This is hitting at exactly 100. And this one's coming short. Any questions so far? We type a few more. 24.24. Oops, too many 2s there. Notice the r squared got even closer to 1. So r squared, the closer it is to 1, the stronger the relationship between the points. The closer to 0, the weaker the relationship. And this got even closer to 1. And it still gives you your equation, which did change some. This y-intercept still 1. The b is still 1, but the slope has changed a little. And notice now, this is moved. It's now at a little over 100. Which is approximately where this one is. Any questions on that? So once you find the growth rate, you can graph this and get your equation that can be used to make estimates. And this being close to 1 tells you they'll be very accurate. The R tells you the same thing. R gives you a little more information. Because it's negative, it means it's decreasing from left to right. If R was positive, it would be increasing. Any questions? Positive. So when we only did a few of them, making an estimate on where it's hitting then is extrapolation. This one's going all the way down to here, so finding 100 would not really be extrapolation because it's almost within the value. But extrapolation is when you go outside of your X values. So right now, looking at our X values, if we went above 56.14, that would be extrapolation. Any estimate in between here would be fine. But if we go outside of that, then it's extrapolation. What that means is, let me write the equation down first. if we write the equation, y equals mx plus b using this m and this b, y equals a negative 0.00. Okay, so I wrote the equation. This is our m and this is the b that was given. I'm going to round this a little so we don't have so many decimal places. I'm going to round to here and get a 1. And because there's so many zeros here, I'm going to round to 1. Now, on a test, I would tell you what to round to. If I didn't, it would be up to you. Now, we went up to 56. So if we make an estimate of a value in here for stock, it will tell us the growth rate. So if we put, what's the growth rate when the stock is 12? This is the stock. And this is the rate. So if we wanted it when, what did I say, 12? If we wanted to know the rate when the stock was at 12, you can just plug it in. And this will give you an estimate. And we know it's a good estimate because our R was very close to 1, or R squared. If you go, well, let's do this first. So it's growing at 88% when the stock is at 12. This is your growth rate when the stock is 12. R squared is a correlation. And it tells you how strong the data is. So if you're looking at R squared, the closer to 0, the weaker, the closer to 1, the stronger. Now, if you're looking at R, it goes from 1 to -1. That way, then it tells you if it's increasing or decreasing. So if you don't have the graph, your R tells you a little more information. And that's why it said a negative 0.999. The negative told us it was decreasing. The 0.99999 told us it was strong. So if you're looking at R, the closer to 1 or -1, the stronger it is. The closer to 0 in the middle, the weaker it is. So looking at R, which is just the square root of this number. So when you take the square root of it, you could have the positive or the negative. So that just tells you if this graph is increasing from left to right or decreasing. So it's up to you which way you look at it. Some programs don't give R. For instance, if we did this on Excel, it only gives R squared. But R gives you a little bit more information. But the closer to 1 or -1, in this case, the stronger it is. Closer to 0, the weaker. Here, 0's weaker, 1's strongest. And if it equals 1, the points are all on the line. These look like they're all on the line, but they're off a little bit. If we look at our graph, I hope I didn't close it. There it is. They're a little bit off. They're not right in the center. This one's right in the center than the first two and this one, but this one's off a little bit. And that's why it's 0.999. If they were all on the line, this would have been 1. Any questions on that? No, if we were, so this is when it's inside or between the values. 12 was between the two values that we had. 12 is between here, right there. That's called interpolation. So interpolation is when you're choosing a value between your endpoints, your smallest and your largest X value. And that, according to this one, our R-square was 0.999. It's going to be pretty accurate. So strong relationship. Extrapolation, you're not sure how accurate it's going to be because it's outside of the values you plugged in. So an example of extrapolation on the one that we did, the graph, let's go with the graph. Anything above 56. So if we did 80, then you would and our stock is our X, then we just plug that into the equation. Now this one might not be as accurate because it's outside of the values we've tested or plotted. It could be accurate, but it's not necessarily guaranteed. So it's growing at 20% when the stock's at 80. But that would be extrapolation because it was outside of the values we used. And it's not as accurate as the R-squared we had. The R-squared, that is for the values between your smallest and largest. It will be that accurate. But it can't guarantee outside of it because it doesn't know what it's going to do. Any questions on that? Okay. Look at another problem. Oh yeah, I showed that. This part here, that's when we looked at the two graphs and saw this is the extrapolation one. We're extrapolating that it will continue this growth and it's hitting below or in between 80 and 100, where this one's hitting at 100. And so that's another way of looking at the extrapolation. but that's what this meant here. And your carrying capacity is when it hits the x-axis. So this one's carrying capacity is 100. This is showing it at around 92, maybe 93. So this is the carrying capacity. Because you hit your carrying capacity when your growth is 0. A molybdenum mine is established to have the capacity to produce 800 million pounds of molybdenum. Molybdenum is essential to your health. Though your body only needs a tiny amount, it's a key component in many vital functions. Without it, deadly sulfites and toxins would build up in your body. Molybdenum is widely available in the diet, but supplements are still popular. As with many supplements, high doses may pose some minor risks, but they're rare. So it is something your body uses. You probably didn't even know because a lot of the foods and stuff that you eat have it in it, and so you don't need to worry about it. Extraction is assumed to follow a logistic model with a rate of 3% and a time step of 1 year. If 10 million pounds have been mined to date, estimate the number of years remaining before the peak production problems. Problems like this can be solved using the time to peak rule. It tells you how long before it peaks. In a logistic growth model for resource extraction with rate R and total extractable resource C, the time left before the peak extraction rate is equal to, and they give you this formula, where M is the total amount of resources that has been extracted. And this is going to give you your time steps. And times was in, this problem was in years. Each step was a year. So we have our equation, but we need to know what the values are. So we know the log D over N minus 1 divided by 1 plus R. So we need to find our values. Where put it? Oh, well. C is the amount, the capacity, which was 800 million. $800 million. M is the total amount of resource that has been extracted to date. So how much did they extract? Of the 800,000, 800 million, 10 million has been extracted. So C was the total amount we had, and they said that was 800 million. And then M was the amount that was already mined, and that was 10 million. The only other thing we need is R, which was our rate. A rate, constant rate, 3% as a decimal. 3% as a decimal, 0.03. Any questions on that part? don't know what I did with my solutions, but. Any questions on that? Now the log button in your calculator. Depending on your calculator. Mine is right here. Now these are base 10 because there's no base written, and that's what a calculator will use is base 10. And then just plug it in. So R was our rate written as a decimal. If you look this up in the book, they actually put it in scientific notation to do it, but you don't have to put all those zeros in, because when you have zeros at the end, you can cancel them, like 3 and 3, 3 and 3, and then even if you wanted to go 1 and 1, so then you have 80 over 1 or just 80. So that this is the log 80 minus 1 or 79 divided by the log 1.03 if we add them. So the log of 79, close the parenthesis, divided by the log 1.03 is 147.8. Now the book said round to significant figures. So two significant figures would be these first two. So it would be 150. Rounding to a whole year would be 148. But they were rounding to two significant figures, so 150. Any questions on that? So it takes, after 10 million is already extracted, it will take 150 years before we hit the peak production. Any questions on that part? We'll do this one next class. There's only like one more problem left in this, maybe two. But I thought it was important to see the graph, and I think it's something you could use in other classes if you have to do research. So that scatter plot is used when you're comparing any two forms of data. Any questions? Okay, if you don't have any questions, I will see you tomorrow.